In this lecture, we are going to talk about some machine learning fundamentals. We are going to talk about generalization, data splitting, cross-validation, and the fundamental trade-off. Let's get started. What is our overall goal in supervised machine learning? In supervised machine learning, we are given some training data. We are given X and Y. We find this mapping function that relates X to Y, and we want to apply this mapping function to predict targets of new unseen examples. For example, suppose you are developing a spam filtering system. Then you are given this training data, you are given some past text messages or emails and their corresponding labels, whether they are spam or not spam. You use that as your training data, you find patterns in your training data, you learn this mapping function that relates X to Y, and you apply this mapping function to predict labels of new examples. So when a new text message or email comes in, you use this mapping function to predict whether that text message or email is spam or not spam. If you have this mapping function, if you have this model which performs perfectly on the training data, but it does a terrible job on new messages, then what's the point, right? We want to be able to predict labels of these new examples accurately. So basically, we want to learn from the past, but ultimately we want to apply it on the future. How can we generalize from what we have seen to what we haven't seen? What we have seen is the training data, and what we haven't seen are these new unseen examples. In our spam filtering example, for instance, what we have seen are the past emails or text messages and their corresponding labels. And what we haven't seen are the text messages or emails which are going to arrive in our inbox. And the main goal of this lecture is to talk about how machine learning tackles this question. In the last lecture, we talked about parameters and hyperparameters and decision boundaries. In particular, we looked at this specific hyperparameter called depth of the decision tree model, which can be used to control the training of the decision tree model. Let's look at this hyperparameter again. I'm using Quiz 2 grade toy classification dataset again. Just to remind you, the target column here is Quiz 2. That is, we want to predict whether a student gets A+ or not, given all these features. I'm creating X and Y, and for visualization purposes, I'm creating this X subset, which has only two features, Lab 4 and Quiz 1. Now let's train decision tree classifiers with different depths. Let's start with depth equal to 1. Now with depth equal to 1, as expected, we get only one split. So this is our decision tree learned by this decision tree classifier, and this is the corresponding decision boundary. We have only one split on Lab 4, and that's our decision boundary. Now, if we look at the error given by this model, that is the proportion of misclassified examples, the error is 0.286. Remember, the error of 1 is the worst error, and error of 0 is the best error. So we have some error here because we are misclassifying some examples with this very simple model. We are misclassifying these red triangles here. Okay, now let's try depth equal to 2. With depth equal to 2, now error has reduced a bit. Now our error is 0.190. Before, our error was 0.286. But with depth equal to 2, we have two splits now. Our model is a little bit more complicated, and we are misclassifying only 3 examples now. In the previous case, we were misclassifying these 6 examples. Now let's continue this. Let's try depth equal to 4. With this depth now, our error has reduced further. Our error is just 0.048. And we are only misclassifying this one example. Everything else we are classifying perfectly. But remember that this is just our training data. So with this model, we are able to classify most of the things in the training data accurately. Now, if we try depth equal to 6, our error is 0, which means that we are able to classify everything accurately in the training data with this particular depth. And this is the corresponding model, which is a more complicated model with multiple splits. So if we plot this max depth on x-axis and error on the y-axis, we see that for max depth greater than or equal to 6, we are getting this error of 0. Okay, so if we train a model with depth greater than or equal to 6, we are going to get this model which classifies each and every example from the training data perfectly. That said, when we have depth greater than or equal to 6, our model is becoming more and more specific and sensitive to the training data. So for example, in this case, if you look at this particular condition, lab 4 less than or equal to 84.5, then we have this condition on quiz 1, then lab 4, then lab 4, lab 4, and quiz 1. So we have this very complicated condition, and it's only based on this one example in the training data. It's there to classify this one example from the training data correctly. So the question is, we are getting this error of 0%, but is it a good thing or a bad thing? Remember that in machine learning, our goal is to predict on unseen examples. We want to be able to predict accurately on unseen examples. At this point, Eva, our enthusiastic learner like you, has multiple questions. I have listed some questions here, and I encourage you to stop the video and go through these questions, think about them, or discuss them with your friends before proceeding. Okay, now let's talk about generalization a little bit more. The fundamental goal of machine learning is to generalize beyond what we see in the training examples. But the problem is that we only have access to this limited amount of training data. We only have access to the training data that's given to us. And we want to learn this mapping function using this data, which would work on these unseen examples. For example, when we worked on our quiz to grade classification problem, we were only given these 21 examples. Now this is a toy data set, so in real life you won't really be working with a data set with only 21 examples. But even if you think about real life situations like spam classification problem, even though you have access to, say, billions of email messages from the past, the possible email messages in the world, they are going to be much, much more than that. So you never have access to the full data set. You only have access to some small subset, some sample of the data set. And with this sample, you want to learn the mapping function that works well beyond the training data. You want it to work well on unseen examples. Let's look at an example. Suppose your learner is shown these 4 examples, these 4 emoticons and their corresponding labels. So the learner studies these emoticons, finds a mapping function, and now the learner is presented with these new images. These are 4 new images, and we want the learner to predict labels for these new images. Now for this first image, it looks exactly like the one we have in the training data. So the learner will be able to predict the target for this, predict the label for this correctly. For the second one, it is a little bit different than what we have seen in the training data, but it's very similar to what we have seen in the training data, just that these eyes are a little bit different. So we can expect the learner to be able to label this image correctly. Now, for the third example, this one is a little bit tricky because it is kind of different than what we have seen in the training data. But if the learner is able to generalize well, that is, if it learns these things, that if the ears are like this, and if it is yellow, and if there are whiskers, then it's a cat, then we can kind of expect it to predict the target of this accurately. Now, in this fourth example, we are presented with this completely new image, which it hasn't seen in the training data at all. So it's a strawberry, and it's nothing like it has seen in the training data. So in this particular case, we cannot really expect the learner to predict the target of this accurately. So the point is that we want the learner to be able to generalize beyond what it has seen in the training data, but these new examples should be representative of the training data. If you present it with a completely new thing, of course, it's not going to get that right. Let's formalize this a bit. Given a model M, in machine learning, people usually talk about two kinds of errors of M. Error on the training data and error on the entire distribution or the entire data set. And what we are interested in knowing primarily is this error on the entire distribution. Because at the end of the day, what we want to do is we want to be able to predict the targets of unseen examples accurately. What we want to do is we want to be able to predict whether a new incoming message in my inbox is going to be spam or not. So we are interested in this error on the entire data set. But the main problem in machine learning is that we do not have access to this entire distribution. And that makes machine learning hard. We only have access to this training data, and we want to learn some mapping function that would work well on the entire distribution using this training data. In the next video, we will talk about how can we approximate this error on the entire distribution given this limited amount of training data.